Greetings and welcome. My name is Brian Waddy, and today we're going to look at the remainder theorem. And it's related to this interesting concept that there's a relationship between the remainder when I divide a polynomial by a particular divisor and when I evaluate that polynomial by plugging in a particular value. And then there's actually a way that we can use division, whether synthetic or long division, as a means of evaluating polynomials for a particular value without having to plug in that value for all of the x's. So let's just jump right into this. So let's see. I think what I'll do is, so let's see. This is the remainder theorem. So if a polynomial f of x is divided by x minus a, let's say. All right, so that's what I'm dividing it by, comma. The remainder is the constant. F of a. All right, and there's technically some more to this remainder theorem, but I just want to focus on this portion of it right now. Let's see. So let's do an example. Suppose I want to calculate evaluate f of 2. If I have this function, f of x equals, let's say I've got 2x squared plus 5x minus 1. All right. So one of the ways I could evaluate f of 2 is just plug 2 in for all of the x's, right? So I could say f of 2 is equal to 2 times 2 squared plus 5 times 2 minus 1, right? And then just PEMDAS my way through this. So 2 squared is 4. 5 times 2 is 10, 8 plus 10 minus 1, that's 18 minus 1 is 17, right? So f of 2 is 17, right? So that's not that difficult, but what this remainder theorem is saying is, what if I took my polynomial, all right, that was this, that's f of x, and divided by x minus a. Now what was a for us? A was the 2. So if I divide by x minus a, they're saying that the remainder should be this 17 that I got. So this is the alternate method, right? So this is method 2. So they're saying if I divide by x minus 2, all right, so if this is my divisor and my dividend was the 2x squared plus 5x minus 1, they're arguing that the remainder should be 17, right? So we'll do long division for now just to practice this. So remember, for long division, divide, multiply, subtract, bring down. I'll quickly review this, but typically we'll probably end up using synthetic division more. And I'll do both cases just to do a quick review. So divide leading term by leading term. 2x squared divided by x is 2x. So I'd write my answer in my x's column. Then multiply 2x times x is 2x squared. 2x times negative 2 is negative 4x. You don't necessarily have to write this example down. And then subtract step, right, because I'm doing divide, multiply, subtract, bring down, right, and repeating. So subtract 2x squared is 0. 5x minus a negative 4x becomes plus 4, so that's 9x, and then bring down the negative 1. So I still haven't gotten to my remainder, all right? So we have to actually repeat this cycle again. Divide, 9x divided by x is 9. So now multiply, 9 times x is 9x. 9 times negative 2 is negative 18. Subtract 0, negative 1 minus a negative 18. It's the same as negative 1 plus 18, which is 17, and that's my remainder. So notice, my remainder I got was f of 2, right? So here's the a that I was using, right? I chose this x minus 2 because I was trying to evaluate 2, right? And I found out that the remainder I get is 17. Okay, let's do the same thing using synthetic division real quick. So if I was doing this divided by x minus 2, I would put a 2 in my little box, right? Because it was always the opposite of that number. And I would have 2, 5, and negative 1. And I don't have any placeholders because x squared, x, and 1 are all represented there. And now what I'll do is for synthetic division, I believe the pattern was add then multiply, right? And repeat. So add the first column is 2, multiply 2 times 2 is 4. Add is 9, 2 times 9 is 18. Add 17, and what do you know? My remainder is 17 yet again. And I think synthetic division is actually the fastest way to do these, especially if I get a polynomial function like a x to the 5th and there's a whole bunch of terms. Synthetic division is the easiest one because I'm using only the operations of adding and multiplying. Where here I had to do an exponent, and then I had to multiply, and then I had to add, and I had to subtract. And who knows, I mean, if this was like 4 to the 7th power, right, that'd be really inconvenient. I wouldn't necessarily know all of these little steps off the top of my head, but adding and multiplying I'm more likely to know than raising something to an exponent. All right, so this is revealing this first concept of synthetic substitution is what we refer to this as. So let's actually write this down. So synthetic substitution. And let's see if I can summarize this in my own words. So synthetic substitution is a process. So when evaluating f of a, instead of doing direct substitution, a in for x and evaluating, we will divide divide f of x by x minus a. So that would look like this. So I would do the a here, because remember it'd be the opposite of that, and then all of the coefficients, whatever those would be, right? So 1, 2, 3, and then the remainder. We'll say f of a equals the remainder. And yeah, exclamation mark, because that is not something we would have suspected to be true. I think that's a pretty unusual outcome. Right? I think that's somewhat bizarre that that happens to be the case. And we're actually going to end up using this method most of the time because we'll end up having quicker calculations that we'll want to be doing, and synthetic substitution is nice because it boils it down to just being repeated addition and multiplication, which are typically operations that can be done more quickly in our heads than exponents and subtraction of numbers and whatnot. So this is the concept of synthetic substitution. I did imply earlier that there was a second part of the remainder theorem, and that actually talks about just kind of an interesting relationship between our answers when dividing. And actually, I'll just write that out here. Basically, what they end up saying is that 2x squared plus 5x minus 1, this, all right, my dividend, will actually equal my divisor, all right, multiplied by my quotient plus my remainder. All right, so kind of just saying, like, as a check, you could multiply these two things and add the remainder, and it should end up equaling what we originally had. We're kind of undoing division by multiplying, right? And then we just have the remainder we have to take care of. Let's see, maybe I can do that just as a quick check. Let's take a snapshot of this. And I will do a check to the first example. Just to verify that it works, give you guys some confidence in what this is saying. So let's actually multiply this out. So x times 2x, right? I'm going to FOIL here. So I'll get, I'll work in purple, I guess. X times 2x is 2x squared. X times 9 is plus 9x. Negative 2 times 2x is minus 4x. Negative 2 times 9 is minus 18. And then I've got plus 17 tagging along. Notice I've got 2x squared. I can combine like terms. 9x and negative 4x will combine to be a 5x. And then the negative 18 and 17 will in fact combine to be negative 1. And voila, notice that this equals that, and it does work out. So once again, if you want to know what that was, we said that the, let's see, what was that? We said the dividend was equal to the divisor multiplied by the quotient plus the remainder. And I don't think you guys can see further there, so I'll just summarize it as remainder. All right, so that's kind of just like a little fact, an add-on, if you will, to this concept of the remainder theorem. But I think that the more interesting thing is this whole concept of synthetic substitution that comes out of it. The fact that whatever our remainder is actually is the same as plugging in a into the function and evaluating it. And that'll end up helping us out later. So there is more to this section called the factor theorem. We'll take a look at that at a later date. But thank you for watching. Talk to you guys later.